Example number 2, determining the probability of events that are not mutually exclusive. So that means that there are some elements in the intersection of certain sets. So, Janik and Violetta are playing a game with 2 dice. If a player rolls a sum that is greater than 8 or a multiple of 5, the player gets a bonus of 100 points. Determine the probability that Violetta will receive a bonus of 100 points on her next roll. And B part, write a formula that you could use to calculate the probability of 2 non-mutually exclusive events. Answer part A again to show that your formula works. So, whenever we're talking about probability, we need to have a numerator and we need to have a denominator. And remember, denominator is the total number of outcomes. So when you roll two dice, you're going to have 6 potential faces on one and 6 potential faces on the other. So that means that you will have a total of 36 outcomes. But the specific ones that we're looking for is greater than 8 or a multiple of 5. So what I'm going to do right now is I'm just going to kind of map out a chart. So here are all the faces. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And let's see what all the different sums could be. So, when 1 is added to 1, we get 2. 2 is added to 1, we get 3, and so on. 4, 5, 6, 7. When 1 is added to 2, we get 3. 2 to 2 is 4, and so on. 5, 6, 7, 8. When 1 is added to 3, we start at 4 and keep on going up. When 1 is added to 4, 5, 6, 7, 8, 9, 10. When 1 is added to 5, 6, 7, 8, 9, 10, 11, and last but not least, 7, 8, 9, 10, 11, 12. So, what I'm going to do is I'm going to highlight some of these favorable outcomes. So in yellow, I'm going to highlight anything that's a multiple of 5. So 5, 5, 5, 5, 10, 10, 10. And now I'm going to highlight anything that's greater than 8. So 9, 9, 9, 9, 10, 10, 10, 11, 11, 12. Now you'll notice that I highlighted these ones twice. That means that they're both multiple of 5 and greater than 8. That means that these are non-exclusive. So I can't just say 1, 2, the number of outcomes are 1, 2, 3, 4, 5, 6, 7, plus the number of rolls that are greater than 8, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, because that means that we will have counted these two twice. So, if I count the number of favorable outcomes here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and take care not to double count, we're going to get a numerator of 14. Because that's the number of favorable outcomes. So, like good little math students in applied, we're going to, whenever we create or use a variable, we are going to make sure that we define our variables. So, we can just do that with a part. So we can say the probability of rolling something greater than 8 or a multiple of 5 equals 14 over 36, or we can say that that is 7 over 18. So now we know our answer. Okay, 14 over 36 or 7 over 18. So now what we're going to use is we're going to use what we know about mutually, or the principle of inclusion and exclusion, to be able to come up with the same answer. So let G represent sums, ooh, that's a weird S, sums greater than 8, and let M represent multiples of 5. So if we were to use the correct notation, we would say the probability of G U M is the number of elements in G union M over 36. And really, well, if I were to be filling in, it would be the number of elements in the universal set. And this one we counted up to 14, and we said that the total number of outcomes could be 36, which turns into 7 over 18. Just for the record, if on, say, a test or a provincial exam you get 14 over 36 and don't reduce to 7 over 18, don't worry about it. That's totally fine. So let's move on to B. Let's use what we know about the principle of inclusion and exclusion to figure out this probability. So remember, they're not mutually exclusive. So we know that it has an intersection, which we can actually see with double coloring here. So if they're not mutually exclusive, then you know that the principle of inclusion and exclusion states probability of A union B. And remember, in the last one we used the number of elements in A union B, but we're going to use the same principle for probability. Equals the probability of A plus the probability of B minus the probability where those two sets intersect, or where those two outcomes intersect. So if we were to use the correct letters in this specific example, we would say the probability of G union M, gum, equals the probability of G plus the probability of M minus the probability of that intersection, G intersect M. This is our double counted piece. So the probability of sums that are greater than 8 are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 out of 36 outcomes, plus the probability of it being a multiple of 5. 1, 2, 3, 4, 5, 6, 7, plus 7 over 36, minus the intersection, so the double counted, or the double colored, 1, 2, 3. Ten plus 7 is 17, minus 3 is 14 over 36. So we have the probability using the principle of inclusion and exclusion the exact same way than if we drew it out and literally counted up our probability. Now, for a lot of people, this method is going to make the most sense, and you just go for it. However, when we don't have a nice visual, it's going to be helpful to use the principle of inclusion and exclusion and apply it to probabilities. Oh, and as a math teacher, I just can't leave it like this. 7 over 18.